Hi, and welcome to the live code example of our method for finding the kappa distribution for assuming a two-layer kappa distribution and measured pressure. This code simulates pressure based on a variety of delta kappa and z naught choices, and then uses that information to pick best candidates for what the underlying distribution of kappa must be based on the measured pressure. So if you haven't seen the short presentation I gave on the definition of the problem statement here, you should go watch that video, or you won't get much out of this one, I don't think. So this finds the hidden kappa distribution, and if a deployment fails, this also has the added bonus that it's going to add a sensor in the layer that wasn't sampled, right? So if I sample the column and there's two layers and I only sample one layer, well, clearly I'm not sampling both permeabilities, right? So it would be best to add a point in the other layer. So assuming that your distribution of sensors is reasonably spaced and samples both layers, we have found that this method generally gives good results. This code shows that if you don't sample both layers, you'd be better to sample both layers. So the main takeaway hasn't really changed throughout our work here, and that is the more sensors the better, the more spread out the better, and you want to sample both layers. So that said, it's using the LSQ curve fit to determine the correct parameters. So if we go help LSQ curve fit, it will tell you right here, solves nonlinear least squares problems, and it minimizes over x, and that minimum is what we're looking for. So let's get into it a little bit. This is the main code. It calls several kind of helper codes, right? So we have get per, this is the forcing that we've applied. Of course, given actual data, we would have to set this to the actual forcing function, maybe the wind or whatever. This is get grid, which is this is all stuff for Trefethen solver based on Dirichlet boundary conditions and Neumann boundary conditions. This is for spectral solving, and get t is just all the time information, right? So the number of steps, the number of outputs, the dt, what we start from. So these three are called in the process of this main code here. So I'll just go through here a little bit. This is how many points we want in how many initial points in phase space. So again, the phase space is z naught d kappa space, and then physical space, of course, is in z. And we're interested in looking at pressure results. And so the setup is simple, right? In the other video, I explained what the problem was. This is us solving for the target first. Okay, this is instead of having a data set that we're applying this to. Right now, we're just showing it to you on simulated data, and so this section is instead of an actual data set, we're having simulated data. And what this does is this gives us a target in phase space for what the two layers are and where z naught is. Again, all non-dimensionalized. And this p action 2 layer here, this tells you basically all this does is take this z naught d kappa, and using the forcing defined in get per right here, p action 2 layer, without getting too long-winded here, is just a code that spectrally takes that Z naught and D kappa and runs it forward to the end, right? It applies. It's called P action because it's the pressure action of two layers given this Z naught and D kappa, and so it gives you the pressure at the final time based on those values, right? So after the evolution, you end up with this pressure target. So now we have a hidden full pressure target, and well, this function is assumed to be measured at several places, but the full function is hidden, and this Z naught D kappa point is hidden. All right, so the elements of our ensemble we're going to go through, and we're going to pick Z points in the vertical. I've picked a total of 10, so this is 10 sensors that are being deployed, and these pick Z points, we assume we space them equally across some subset of the column, and then the data values, which are assumed to be known now, are this last half. This doesn't return just the last pressure output. It returns the entire pressure for the last half of the number of outputs chosen. Why do we do this? Well, basically what this does is this now provides an entire data set, right? That's why we call it data values, right? So this is the last output. This is the output right up to the basically the whole last half, but only at the picked Z points, right? So now we have this was just one pressure target, which is the full function everywhere in Z at the last output. Now we have the data values at the deployment locations and over the entire last half of the simulation. We picked last half because we want to get rid of any transients introduced by the initial conditions. All right. This is just the code that adds a point to the other layer if you missed one of the layers. And now we're going to plot all the data. And here we get into the meat of the algorithm itself. So this is so for the number of initialization ensembles, again, so this is how many points the number of ensembles is how many different tries we're going to do. The number of initial ensembles, this is how many points in phase space we're going to try. So I'm going to come down here. I'm going to start at some reasonable Z naught and D kappa. I don't know if it's right, but basically I'm going to use nonlinear least squares, as we said, from LSQ curve fit, and I'm going to using P action two-layer last half, which is again looking at the pressure action on what pressure do you get for the whole last half of the simulation given the X naught. So we guess some X naught, we use this as the function, and we look at pick Z points and all the data values as the initial information, and LSQ curve fit is going to iterate and give us an X, which is a point in phase space, and so this is for the original deployment, and then this is for the added point deployment. Same kind of thing. You can think of it as kind of a gradient descent, although it's more than that and tries a couple different algorithms. Okay, so that's great. It gives some answer, and now we go through and we plot these. I'm not going to run the code live because it takes a while, but once the dust clears, this is an example of something you'd have. Okay, so here is an example in phase space. So we have delta kappa and Z naught. We know that the answer is actually right here, plotted in red. And you can see these all these green lines. This is from a deployment where it wasn't sampling both layers. Okay, so let's go to this. This shows this deployment. So this is the pressure function, and this is Z, and this is pressure. Okay, and the target is in red here, and the target has been measured at the red points, which are in the blue circles here. The target with added point, well, that just means that this is the point that's been added to improve the deployment. And so if we zoom in a little bit here, you can see that the initial deployment is over, a small subset of the Z extent, and these equidistant 10 points are right here. And so these are the original deployment. These correspond with all these green points in phase space. So all these different points have all these points from the original deployment have converged in phase space to all kinds of wrong answers. You can see them spreading out all over the place. And you can see too, if you zoom in some more, again, ignoring the blue dotted lines for a moment, you can see that there's all kinds of other wrong answers for the green right here. You can see those all in the green circles. Maybe I'll zoom in a little bit more for these. So you can see there's a ton of wrong answers here from the deployment that did not sample both layers. Okay, so you have all kinds of, so these are all the initial points, the ones that don't have circles attached to them. And you can see that the green are converging all over the place, but a lot of them are not going to the right answer. Some of them are, but a lot of them are not. Okay, so what happens when we add the other point? Well, you can see the other point right here. You can see the other point that's in the other layer. Remember, Z0 is at 0.8 here. And so we've added a point in the other layer. And actually, before I go on to that, all these points that are converging to wrong answers, every point there corresponds to one of these many curves that is also the wrong answer for pressure, right? So remember, every point in phase space results in a pressure curve. And you can see that by converging to the wrong point, there's a lot of incorrect pressures, a ton of them, in fact, right? So let me zoom all the way out again. You can see you have this pressure over here that's way off. You have this pressure over here. And again, ignoring all the dotted blue lines for now, you have lots of answers, and they're mostly wrong. There's some, they're kind of clustered for the most part around the right answer, but there's also some big wrong answers. And of course, if I zoom all the way out, you can see that some of the answers are spectacularly wrong. Okay, so in particular, Z0 is not a negative number, so all these are trash down here. Okay, so clearly the deployment did not necessarily capture good delta K, good Z0, did not give plausible answers to our question of what is the underlying two-layer distribution. However, when we add this other point in the second layer, because remember it's at 0.8 here, so this layer is sampled from 0.8 down. Now we added the blue. What do we see from the blue? Well, still you do occasionally get a bad one, right? So you have here, 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 and here. So remember, there's like 300 points, and I can immediately pick out, 5, 6, maybe let's say 10 or 12 that still went awry. However, when I zoom in here, what we see is, for the most part, I can see that, okay, yeah, I have some ones that are converging away, but mostly blue lines start where they should, and yep, they converge into the main point. So for the most part, adding the extra point has caused the vast majority of ensemble members to converge there. So here we've added the extra point, and you'll see now that the red line is, and the dotted line here in the blue corresponds to the pressure that we found. And the match is pretty good. Now, occasionally you still get an error. Like I said, there's one. But I think you'll agree that if, 290 out of your 300 points line up on one curve, you're going to be pretty confident about it. That's in distinction to all these points in the green that are escaping to the wrong points. Which of these curves is right then? Because you've almost filled it in. There's so many curves here. Which of these curves is correct? You don't know, right? Because remember, all these curves go through all these points in your deployment, so you don't know which one you've measured, and then of course you don't know which kappa is correct either. So that's a brief rundown of our guess kappa method. There's a fair amount going on. You really have to think a little bit about what it is that you're trying to find. But remember, we're trying to find, assuming a two-layer model, we're trying to find where the interface is in that two-layer model, and what the difference between the permeabilities of the layers is. And that's our parameter space. And this is a method that shows our parameter space exploration and shows that it is better to sample both layers. And in other cases, we've also shown that it's better basically to spread the points out, which I think you can see is plausible here. You can imagine that if these points here were spread through the entire column, say you had 10 points and they were spread pretty much evenly through the column, well, then you could differentiate between all these green curves that are here, right? But because there's only one point, and in fact, before that point was added, in this deployment, there was no points over here, well, then you have a real problem, right? Obviously. So all that just to say that it is best when you're doing your deployment of your sensors to make sure that you have as many as possible, that they're spread out, that they're sampling any layers that are involved. And then using this kind of method, you can run many ensembles and gain some confidence that you do actually know what the permeability in the pile is based on what you can measure, which is the pressure. Thanks for watching.